Uh, okay. Today our speaker, Edmond Tingtao Zhou, is from California Institute of Technology. Edmond received his bachelor in physics from Peking University in China, and then he pursued his PhD in physics at MIT, focusing on material sustainability by understanding how phase transitions in porous colloidal media lead to materials degradation. And then currently he is a postdoc fellow at California Institute of Technology, combining statistical physics and fluid mechanics to study the fundamentals of living matter and its applications in biomedical and responsive materials. Today, he will give us a talk on the hydrodynamic interactions impact destroying motility-induced phase separations in active suspensions. Okay, Tingtao, you can start now.
Yeah. Okay. Yeah. Thank you. Thank you, Haichan, for the kind introduction and inviting me. Uh, yeah, I'm very happy to be here and discuss with you about our recent study on the role of hydrodynamic interactions in specifically in motility-induced phase separations in active suspensions. If you're interested in more detail of the work, we have this preprint online available. I'm currently a postdoc with John Brady group at Caltech. Okay. So I guess we don't need to talk too much about the introduction about active matter here for this audience. I guess people are here or experts in the field. So I'll just briefly say a few words of my own kind of perspective on it. I feel to me active matter is a interesting is a lens where we can look at all these familiar living systems through it, right, and discover some new physics. These active matter systems, they are interesting. They are intrinsically non-equilibrium, and this field turns out to be a very interdisciplinary field, right? So people coming from all kinds of different backgrounds, but we all share the common language interest here. So it's a very cool field. And I think it's also a very challenging field. So, of course, first of all, these systems are non-equilibrium. So, how do we describe them in a proper framework of non-equilibrium statistical physics? That's always the central topic when we study active matter. But also, for me, one specific challenge is the fluid mechanics perspective in active matter. Um, and as we know, the fluid mechanics at microscopic scales are long-range interactions. If you look at the Stokes flow, the fluid mediates an interaction that can go up to like millimeter scale. While if you compare to typical colloidal interactions, that's on the scale of nanometers. So these are long-range interactions. And these interactions are also many-body interactions, meaning that if I add a particle number 3, then it will change the effective interaction between particle number 1 and particle number 2, right? And uh, it can also be non-reciprocal interaction, meaning that particle number 1 can be attracted to particle number 2, while number 2 is at the same time repelled by particle number 1, right? So it's a wicked interaction, and I think that's why it's not so easy to deal with it in a lot of cases. So today, I will focus on understanding the effects of these hydrodynamic interactions in active phase separation. So just in case, let's warm up a little bit first with something we're familiar with from our undergrad, how we think about passive systems, phase separations in passive systems. So we probably recall the name of van der Waals if we think about phase separation, right? And if any students you don't, that's fine. You don't need to worry. So the key idea of van der Waals is basically to think that if we know how the pressure of the system depends on the density, then we can actually predict phase separation from a mechanical perspective. So why is that? Let's take a look at a simple equational state of van der Waals liquid. Basically, there are two terms in the van der Waals pressure, right? The first term is a excluded volume repulsion, right? That just comes from the excluded volume interaction of the molecules, and that's a repulsive component. And then on top of that, we're going to, van der Waals also introduce a short range attraction between these molecules, right? So that's a attractive force. And if we combine those two, we get this equational state. So the interesting thing is if we start at a high temperature above a so-called critical temperature, then the pressure is a monotonic curve of the density. All right. So mechanically, everything is stable. There's no phase separation. And if we decrease the temperature all the way down to below the critical temperature, then at some point, the pressure curve will become non-monotonic, all right? And then we're going to have a region in where the pressure curve, the derivative of the pressure with respect to the density is negative. And that indicates a mechanical instability, right? Because that means if I think of a small volume of the gas, and if if there is some density fluctuation such that this small volume becomes a little denser, then the pressure actually drops, right? So this small volume will be compressed by the surrounding gas and keep shrinking. So that's an instability mechanically, right? So that's easy to understand. And that's van der Waals criteria for phase separation, all right? So yeah, that's the passive liquid gas phase separation classical theory. So how about we add activity to the system? Now let's forget about hydrodynamics for now, just dry active matter, right? So people have made a lot of progress theoretically to understand how phase separation works in dry active matter. So let's first talk about maybe the simplest model of dry active matter, which is what we call active Brownian particles. All right. So an active Brownian particle is simply a sphere that propels itself along a direction q at a velocity u naught, right? And the direction q will drift over time diffusively over a typical timescale of tau r. And the dynamics of the active Brownian particle is simply described by this overdamped Langevin equation, right? So there's a self-propelling force, zeta u naught, and possibly a Brownian force, and then the particle interaction force, right? And angular momentum balance will determine how the orientation drifts over time. So there's a typical scale, length scale, besides the size of the particle, which is L naught, and we're going to call that the run length of the active Brownian particle. So the interesting thing is, even if we do not include any attractive interaction between the particles, all right? So here the particles, they only interact with excluded volume repulsions. However, if we put enough amounts of these active Brownian particles together, if the density is high enough, activity is high enough, they can spontaneously phase separate, as what you're seeing here on the right. That's my own simulation, right? And why that happens, you could think of it. I think an intuitive way to think of it is a traffic jam. So imagine if I put a bunch of Roombas all together in a crowded space, right? They're all moving at their own will, and if the density is high enough, then they get stuck together and have a traffic jam, and they cannot get out of it easily. So that's why you have this kind of interesting phase separation. And people have observed a similar phenomena, for example, in these bacterial colonies. And of course, for real bacterial or biological systems, there are a lot of more factors that we need to consider, right? But this phenomena is not only theoretically interesting, but it can be also very interesting for many applications as well. And to stress the intrinsic non-equilibrium nature of the phenomena, I'm going to stress again that there is no interparticle attractions here, but only repulsion between the microscopic particles. So
Hi, Tingtao.
yes.
So in your own simulation, the color map shows the density.
So yeah, so here the color shows actually the local crystalline order.
Oh, local crystalline order.
Yes,
Okay, so I
yes,
see
because
some
the
kind of straight lines and some dots.
yes,
In
those are the crystalline defects actually.
okay, okay,
Yeah, yeah, because this simulation is a monodispersed particles. So that's why when they form the dense phase, they're going to basically crystallize.
okay. Thank you.
Right. Okay, there are many ways to, well, there are a few ways, I guess, to formalize this idea and describe the phenomena of motility-induced phase separation mathematically. I'm going to take one of them. Basically, we can start with a microscopic transport equation, right? So we think about how the probability density function of the n particles evolve according to time. So here, microscopically, we need to keep track of both the spatial and orientational degrees of freedom, right? That's why I would have both the translational flux JT and the rotational flux JR, right? So now, we're not really interested in this many-body probability density and keeping track of all the orientational degrees of freedom, but rather we want to measure something simpler, such as the number density and the polar order, right? So we can define them as the ensemble average over the orientational order, right? The orientational degree of freedom. So can define all these coarse-grained fields all the way up to many higher order terms. So now if we after defining these terms, if we coarse-grain over the orientational degree of freedom, then you end up with a hierarchy of transport equations for these mean field variables, right? And as typical in a kinetic theory hierarchy, the transport of the number density n will depend on the polar order m, and the transport of m will depend on the nematic order q, and so on. So it's an infinite series, and we have to typically cut off at some point. So here I'm going to just cut it off and say that we're going to neglect any moments higher higher than the nematic order. So I'm going to say there's no nematic order and approximately solve it. So if we do that, we already can see some physical meanings of these terms. Here we see that the transport of the number density will involve the gradient of the collisional pressure, right? So that's the familiar virial stress between the particle interactions. There is another term if we solve the polar fields in terms of the number density. There's another term that appears, which is what we call the swing pressure. All right, and the swing pressure here is proportional to the self-propulsion, the number density, and also the effective run length of the ABPs. So after we solve those equations, then we can do some very simple linear perturbation to see the instability, right? And that modifies. Now we see that we get a modified version of the classical van der Waals criteria, where in the van der Waals criteria, we will only have the particle collisional pressure in the criteria, right? Except now here, because of the activity of these particles, we also have the new component pi s swing pressure, but the same framework applies, right? Okay, so based on this spinodal criteria, uh, people can also map out a phase diagram for the active Brownian particles. So for example, here is a phase diagram that's already mapped out from simulations. If you are inside this light green area, then that means we're going to have a liquid gas coexistence. So we will have MIPS in this region of the parameter space. Okay, so seems that we're somewhat satisfied that we can extend the classical van der Waals theory to understand why dry active Brownian particles can phase separate spontaneously. Okay, so now let's think about what will happen if we include hydrodynamics. So first of all, why do we want to include hydrodynamics? And that's because for a lot of active matter experiments, uh, mostly for any kind of micro swimmers, it's done in a water environment, right? So if we want to do the experiment with genus particles or some bacteria or other micro swimmers, they're always in the water. And we know that water makes a difference, right? So, for example, people have it's been known that if you ignore the fluid phase, then, for example, your prediction for the gelation structure will be completely off. Okay, so water is important. However, so far there seems to be some ambiguities or controversy in the literature in terms of what will happen if we consider not dry active Brownian particles, but if they are immersed in water. So here I'm just listing a few of them. For example, in Sentinel and Shelley, their theory would predict if you have a dilute suspension of so-called pusher swimmers, you should observe active turbulence, all right? And in another work from Susan Fielding's group, they studied so-called squirming disks model, right? And they observed that MIPS go away. While in other works from Ishikawa and Pedley or Zalto and Stark, they observe clustering and coherent structures and so on. And a lot of more interesting structures have been observed. So, however, so now the question is, which one is the correct one or the true one? However, these all of these simulations previously done was kind of small, right, on the order of 200 particles. So it's hard to know for sure what would happen if we scale to large systems. And the true answer might be that they all observe the true thing, however, just different aspects of the same phenomena. So here's how we're going to approach the problem. Let's first think about a simple problem. Just start with one passive colloid particle, right? So how do we describe the hydrodynamics of this colloidal particle? That's pretty simple. We write down the Stokes equation for that. And incompressible, we assume the fluid phase is incompressible, and Reynolds number goes to 0, so the equation is linear. And suppose I apply external force to this colloidal sphere. I ask the question, what would be the velocity of the colloid, right? So basically, I have a force balance between the applied external force and the hydrodynamic drag force on this particle. So because the Stokes equation is linear, we would expect a linear relationship between the drag force and the velocity, right? And that's exactly what the famous scientist George Stokes has worked out, and known as the Stokes drag. So what about if we have many particles? Now, this time, we can simply extend, again, the equation, Stokes equation is still linear, so we can simply extend this equation for the drag force. Instead of having one scalar of the Stokes drag, we're going to have a so-called resistance matrix, or FU. And it's a many-body effect. So we're going to call it grand resistance matrix. And the interesting thing is this resistance matrix only depends on the geometry of the system, right? Basically, if I know where the particles are, their positions, then I know what should be the resistance matrix. And then we can work out the dynamics from it. So this idea has been developed into the Stokesian Dynamics framework, all right, where we could include not only the linear velocity, but also higher order velocity moments, and solve it from once we know the resistance matrix, then we can solve it. So that's for the passive colloid. Now we want to have activity, right? We want to have an active swimmer as well. So a classical framework to model an active swimmer is a so-called squirmer model, all right? A squirmer is a sphere where we're going to prescribe the surface slip velocity on the sphere such that this sphere is going to propel itself and move, all right? So that's how it moves. And mathematically, we can also do a spherical harmonic expansion of the surface slip velocity to all kinds of orders, right? And to the linear order, we have the self-propulsion speed, US, and the second order, we're going to have a strain rate, ES, and so on, right? So this is actually how we do it. So I'm calling it Active Fast Stokesian Dynamics method. And to make it, of course, to make it accurate and fast, there are a lot of implementation things that we need to worry about, but we don't need to worry about here. It's taken care of. So let's use it and see what happens. So for now, I'm going to ignore all the higher order moments and only keep the first order moments, which is the swim velocity, US. And if we do that, we get a so-called stealth swimmer. So the stealth swimmer, basically, we prescribe the surface slip velocity all to the same direction, such that when it swims alone, it's as if the water just passed through the body. All right. So when the stealth swimmer is moving alone, it's only moving at a constant speed, but not disturbing the surrounding fluid. Right. So you ask, where is the hydrodynamics then? The hydrodynamics comes when two of such stealth swimmers come into collision, right? For example, if we have, as shown here, if we have these two swimmers swimming towards each other, then the excluded volume repulsion is going to create a force pair, right? And that's a force dipole. Also, to be more precise, it's a pusher force dipole, right? And this force dipole is going to create a flow field that goes like that, right? So if we zoom out to the far field, if you look at the right hand, the picture on the right side, the far field flow is a dipolar flow, which decays as 1 over r squared, long range flow, and has both translational and velocity and also vorticity. So to show this, we can look at this example. So in the video, I'm simulating two stealth swimmers in a head-on collision. So these two purple particles, they are stealth swimmers. Before they collide, nothing happens. The yellow particle is a passive colloid. The passive colloid didn't move before they collide, but once they come into collision, they generate a force dipole, and the dipolar flow attracts the third particle in this case, because third particle is because of the exact position of the particle. So that's the hydrodynamic interaction for these stealth swimmers.
Can I ask a quick question over here?
Yeah,
Regarding the
sure.
example that you just showed. Why is it that only upon contact the dipolar flow, sort of the pusher-like flow, kicks in? Is it
Yes.
there's a contact? Is there no, the repulsion has no tail? Or is it only what kind of repulsive interaction there is? Is there at finite distance, do they repel? Do these particles
Yes. Here
contact?
it's basically a very short range. Here is basically hard sphere repulsion.
I
So
see.
that's why, yeah, it's almost only. Of course, in the simulation, you cannot really do hard sphere, right? Typically, you have a little bit of interaction range. Yeah.
Yes, but the moment you are within that interaction range, then
Yes.
the pair behaves as a pusher, and you have
Yes.
the stress generated. Okay, thank you.
Yes. Exactly. Yes. Yeah. So once, yeah, as you just said, once any repulsion force kicks in, right, then you form this force dipole, and that creates a dipolar flow, right? So this is from a force perspective, but you can also think of it from a directly from the velocity perspective as well, right? If you don't like the force perspective, because we just said the stealth swimmer, we prescribe the surface slip velocity in this example. The slip everywhere on the sphere is going to the left, right? So now for this, that's exactly this particle. So this particle, if we look at the left part of the particle, the velocity goes to the left, while on the right particle, the surface slip is going to the right, right? And these two particles, they are equal, so they are stopped by each other, right? So, but we still require the surface slip velocity going in that direction. So that also tells you it's a dipolar flow. Yeah. Okay, so let's have some fun and look at what happens in the simulation. Okay, so I'm going to just play the simulations. Oh, yeah. So let's pick a point. Let's pick a point in the parameter space where we predict there should be phase separation without fluid. All right. So we're deep in the phase separating part of the phase diagram. So this is what happens. On the top row, you're seeing the stealth swimmers, right? And on the bottom, you are seeing just dry active Brownian particles. And so in every simulation, we're simulating 10,000 particles. So it's a pretty large system. And also, I want to mention here, of course, you can tell that we're simulating monolayers of these active particles. But for the stealth swimmers, the fluid is 3D. So it's not a 2D situation full of fluid. We always have 3D fluid. Okay. So as you can see, the active Brownian particles, they phase separate as we expect, right? That's no surprise. But the stealth swimmers, they do not. So we can keep running these simulations and videos for a very long time, but these density fluctuations, they never coarsen. Okay, so they're just density fluctuations, but no macroscopic phase separation. Okay, so it looks like hydrodynamic interaction will destroy the phase separation.
Can I again ask another quick question over here?
Sure.
Maybe you will answer this later. What happens when you change the dimensionality of the fluid?
Yes, I'm going to, yeah,
Okay.
I'm going to talk about that later.
Okay, I'll wait for you to talk about that then.
Yeah,
Thank you.
okay. So Okay, so just to reassure us, right? We can also start a simulation from a dry MIPS configuration, so it's already phase separated. But now we click our finger and say we turn on the hydrodynamic interaction, right? It dissolves, all right? Okay, so let's try to understand what's the mechanism here, right? So as we said, the stealth swimmer does not disturb the fluid and does not generate any flow when they are swimming alone, right? But when these stealth swimmers come into collision with each other, they are going to form these pusher-like force dipoles, and that will generate dipolar flows that are long-range flows. So suppose we look at one of the particle here, and there are collisions happening elsewhere, right? So that collisional dipole is going to generate a flow which propagates to the third particle, right? And then this flow is going to affect both the translational and the rotational velocities of this third particle, right? So if you have other pairs of collisions, they will contribute their own flow, right? So you have to add up all these flows together. So let's first try to understand separate the effects of the translational velocity and rotational velocity, right? Which one is the culprit, we can ask. So let's first only keep the rotational velocity, but remove the translational hydrodynamic velocity. Actually, I want to add a comment. So we can do that in theory. So I don't know how to do it in experiments, right? But we can safely separate the translational velocity and the rotational hydrodynamic velocity for spherical particles. Okay, so for spherical particles, we can in theory assume the particle is somehow can have a time varying surface slip velocity, right, to compensate. So you can do that. Okay, if we only keep the rotational hydrodynamic velocity, what happens is now the correlation time for the orientation will be affected, right? And we can estimate that in a self-consistent manner. And that's if you consider the correlation time, how that's affected by the collisional dipoles, then you can come to this simple formula. And it seems a good fit with my simulation results, at least when the density is not too high. But you will notice that, of course, the rotational diffusivity will always be enhanced, right? Because everybody is making me rotating to a certain direction. So you add up these random rotational vectors, right? That will give you an enhancement in the rotational diffusivity. And that, if we try to map that back to the idea of the dry active Brownian particles, that means these particles are rotating faster than they should be, right? So that's a stabilizing effect. And we can mathematically we can calculate that, right? So I will talk about. I can discuss more details if you want later. But here, to be more precise, we need to modify the swim pressure a little bit. All right, and we need to do this integration over these quantities to get a proper swimmer modified swim pressure, and we put this measured rotational diffusivity into the modified swim pressure, and together with the collisional pressure and another piece coming from the hydrodynamics itself, okay, then we get a total pressure. And this time, the total pressure, the red curve you're seeing here, actually becomes monotonic. All right. And we just said that if we have a monotonic pressure as a function of density, here the packing density, then the system is stable, right? There should be no phase separation. So that's why we're seeing these non-phase separating simulations. All right. Okay. So basically, we can conclude that the rotational hydrodynamic velocity is making these particles rotating faster than they should be, right? So effectively reducing the persistence of the active particles. And that's why, and effectively reducing the swim pressure as well. And that's why they do not phase separate. And this this observation is consistent with the squirming disks model from Susan Fielding's group, right? Okay. Now let's look at the other candidates, the hydrodynamic translation. All right. So this time we do not. This time the particles' rotation will be determined intrinsically by their intrinsic persistence, right? But not affected by the hydrodynamic interactions. But their translational velocity is affected by the hydrodynamics. Okay. It turns out in this case, we have a more subtle effect, and that confinement, or as Suraj just said, mentioned, asks the scale of the fluid actually matters, right? So a simple way to model that, we can consider a liquid film. Okay, so it's a liquid film as shown here on the right. So in this case, we have liquid air interfaces, both on the top and bottom, right? At these interfaces, we will have stress-free boundary conditions on the parallel to the XY plane, right? And no flux boundary condition in the Z direction, all right? And we can introduce a new dimensional non-dimensional quantity, which is the ratio of the thickness of the liquid H over the radius of the particle A. So mathematically, this system is particularly convenient because the image forces just form a infinite periodic array. Okay, it turns out to be very convenient. Okay, so let's look at the simulation. On the left, you have a strong confinement. All right, so H over A equals 10. So the liquid film is only a few times thicker than the particle size. On the right, you have almost full 3D fluid. All right. So they turn out to be different. When we have a truly 3D flow, right, on the right side, again, phase separation disappear. But if we have strong confinement, if the liquid film is very thin, then the initial dense cluster will dissolve, but then a new dense phase will form again, right? So meaning that it's actually a stable, it's actually a very robust phase separation. Okay, so why do we observe this? I want to first mention that the first idea is, of course, to think of the translational diffusivity, right? But it turns out, if you look at the numerics, the translational hydrodynamic diffusivity is very small, always very small. So that's not the case. So we need to think about maybe there is a convective effect instead of diffusive effect, all right? So if we think about any convective effects, there actually is possible to be a circulation flow confined between the two liquid air interfaces, right? So if you consider such a pair of collisional dipole, right, it can draw fluid from above and below the XY plane, and then the fluid can go out in the XY plane. So the three-dimensional flow field is incompressible, but the components in the XY plane does not have to be incompressible, right? So there can be a net flow jetting out from the dense part, okay? And that flow, and if we generalize the idea of collisional dipoles into a dense cluster, then in the continuum limit, we can write the flow is driven by the gradient of the collisional pressure. All right. So let's understand the characteristic of this flow. Okay. And we can again try to we can do that by finding the fundamental solution, the Green's function of that. So suppose I have a point force. What's the flow, right? So it turns out because of the periodic periodicity of the image system, we can solve this by a Fourier series. I'm going to only show you the results. I will skip the derivation. But it turns out you have a Fourier series which composed of these modified Bessel functions, and they decay exponentially, right? So actually, the zeroth order term does not decay exponentially; it decays algebraically, but that term will correspond to a pure 2D flow, and that will disappear if you have actual symmetry. So if you consider a circular disk, circular dense cluster, then that will not happen. So we can ignore that part, while the leading order flow then will be decaying exponentially in the xy direction, right? And they will decay on the scale of the confinement scale, h, right? So that motivates me to model it as a local effect. So I'm going to say effectively, that means I have a local flow. If I zoom out and coarse grain, right, then there is a local flow proportional to the gradient of the collisional pressure, and the strength of that flow is proportional to the width, to the height of the liquid film, right, the scale of the fluid. So we can take this flow and put that into the transport equations for the number density and the polar order, right? And just solve these equations. All right. So again, this physically what happens in this simple model is that whenever I have a dense phase, I'm going to generate a flow at the edge of the phase, and that flow is a local flow on the scale of h. And we're going to smooth it and say the average strength is proportional to that. So we define alpha. So let's solve a simple 1D model, right? So assuming actual symmetry, if I have alpha equals 0, that means I do not have any flow, which is dry active Brownian particle, right? And that's what happens as you expect. We have this black curve, which is a phase separation curve, right? So this curve corresponds to the configuration on the left, where you have a dense phase in the middle, right? And then dilute phase on the outside. Now, if I keep increasing the strength of the flow, or in another word, increase the thickness of the film, H, right? Then as you can see, these curves, they gradually become more and more flat and eventually become just totally flat, which means this simple model predicts that the dense phase will go away. So you will have just homogeneous phase, so no phase separation, right? So that captures, the simple model seems to capture the essential feature of the system. So again, when the thickness is large, right, when the flow is 3D, then you can have a net flow in the xy plane, and that destroys the phase separation. But if you have strong confinement, then that flow will eventually become too weak to prevent phase separation. Okay. Okay, another interesting consequence of this, if we think this is true, is that again, as we said, the reason why we can have the net flow that destroyed phase separation is because the 3D flow is incompressible, but the component in xy plane does not have to be, right? So we have this effective compressibility of the fluid, right? But if we have a truly 3D situation, then the flow is incompressible. So there should be no net flow possible, right? And we can only conclude that there should be phase separation, right? And indeed, that's what I observe in the simulation here. So this one is a 3D simulation with only translational hydrodynamics, and indeed, they phase separate. Okay, so far, it seems that we understand that if we include full hydrodynamics, by that I mean both the translational and the rotational hydrodynamic velocities, then that will always destroy phase separation, all right? And either the translational or the rotational hydrodynamics alone can destroy MIPS. So both of them are possible to destroy MIPS. But I'm going to give a twist on the story. In many previous literature, either in simulations or in experiments, people have observed clustering, okay, in different contexts. So why does that happen? Because we think right now at this point, we'll think whenever you have full hydrodynamics, it should destroy any such macroscopic clustering. So one idea is that what I think is happening is that in real experiments or in the simulations, you have physical walls and boundaries. So what if the swimmer is actually swimming towards the boundary? Okay, then they're going to collide with the boundary, and again, this collision will introduce another type of collision-induced dipoles, right? And that will induce again a dipole of flow. But this time, if the swimmer is swimming towards the wall, the dipole of flow will be attractive, right? Like this animation is showing on the right. And that effective attraction, hydrodynamic attraction, can be responsible for the aggregation that we observe in this literature. Okay, so to sum up, we think there are two types of collision-induced dipoles we should consider in a real experiment or simulation with boundary, right? So we need to consider the swimmer-swimmer collisions and the swimmer-wall collisions. And now we understand the mechanism, how it works. We can even leverage and tune the strength of each component, maybe to allow us to control phase separation or in general, more general patterning. Okay, I will now give a final remark, which is a simple idea on how to recover MIPS in water, all right? So we just said that if we include full hydrodynamics, then there's no chance to have real MIPS, right? Like pure motility-driven phase separation. But there might be ways to mediate the strength of the hydrodynamic interaction, all right? For example, we do not have to have the same radius for the hydrodynamic interaction as well as the excluded volume interaction, right? So let's imagine if I can put some brushes on the surface of these active swimmers, right? Such that the excluded volume radius B is much larger than the solid fluid interface A, right? Then in this case, what we are doing is actually we're going to dilute the density of these active swimmers, right? And that will lead to, that will weaken the rotational hydrodynamics. And then if we confine them in a thin film to weaken the translational hydrodynamics, right? Or in a truly 3D situation where the translational hydrodynamics alone cannot destroy MIPS, then we can possibly recover phase separation, right? So here is a demo simulation where I have strong confinement, H over A is 3, right? And I put the excluded volume radius B to be twice of the liquid-solid interface A. And it seems to work. So yeah, as you can see, the dense phase keeps coarsening, right? And yeah, so if I run it for longer and longer, yeah, the dense phase will eventually coarsen and form a macroscopic phase separation. Right. Okay, so that's what I have to say. And if you have more questions, I'm happy to answer. Yeah. Thank you.
Great talk. I have a question.
Yes.
So for the rotational HI and the translational HI, both destroy the phase separation. But when I see these two movies, I feel that by eye, I feel there are some kind of difference in the dynamics. One being kind of the clusters, small clusters being more kind of changing more frequently, while the other one for the translational one, the small clusters kind of, I mean, do you have
Ah,
any kind of quantification to measure? So what's the difference between the effect of translational and
I see.
rotational HI?
I see. Uh, I actually I don't think there are appreciable differences between them. I think here the visual difference is because I use different speed for the
Oh,
video. Yeah.
okay, okay,
So I should probably use the same playback speed for them. And actually, I wanted to show different initial configuration, right? So as you can see, the left one start from random configuration and right one from the dense phase separated configuration. So yeah, but if you look at the right one, like if you keep staring at it, actually they're also fluctuating.
okay.
So yeah, so I think they are yeah, qualitatively I think they are the same.
So, okay, thank you.
I wanted to ask about the first about the dimensionality. So you have this parameter h over a for the confined but 3D fluid, but the particles are strictly in the XY plane. Is that the idea?
Yes.
Have you looked at the sort of case intermediate between that and your fully 3D simulation, where it's still relatively confined, but the particles can hop over each other in like 2 or 3 layers?
Yeah, I think that's a great idea, and that's something I'm currently doing. So I'm currently putting instead of simulating. So here I didn't want to do that because here I have liquid air interfaces, right? So if the particle is hitting that interface, then more complicated things can happen. You need to consider maybe the surface tension, the capillary waves, and so on. So I didn't want to do that here. But I'm doing hard plane walls on the bottom and right and upper, and so in that case we can see this kind of quasi 2D, right? Like what you described. And actually, in case we are interested, so one of the key literature I found was from Zalto and Stark. So their simulation was actually this case. So they actually put solid walls on the top and bottom, and they allow the particles to move and rotate 3D. Yeah. So in that case, they actually observed aggregation, right? Like in this picture. But they also observed that these particles actually hydrodynamically, it also favors when the particle is pointing into the wall. So that's what they observe in their simulation. So that's why I think, what they observe is probably this hydrodynamic attraction instead of the motility-induced aggregation.
I see. My line of thinking was that the original motility-induced phase separation, I think, came from the field theory approach, where you have a scalar field rather than these active Brownian particles. But the
Yes.
disconnect there is when you imagine the scalar field of particles globbing together and slowing down, that there's sort of a continuum nature to that, and then the active Brownian particles in 2D are just discretely bumping into each other and sterically repelling. But if they're able to overlap a little bit into the third dimension, that might get you closer to the field theory in the
I see.
agent-based dynamics. Just a speculation.
Okay. Yeah, I haven't studied the field theory approach systematically. Yeah, but of course, in the simulation, that's something we definitely can do. Yeah, and that's in fact what I'm doing right now. Yeah,
Awesome. Thank you.
yeah, thank you.
There is a question in the chat. Wu, would you like to ask by yourself? Unmute.
I have a hand up. Is that all right?
Oh, yeah, you can ask first.
I was going to ask. Well, I'm Tim Pedley, by the way,
Hi, Tim.
in Cambridge. The results you showed towards the end, and thinking about changing the boundary condition on the squirmers, makes me remember that when modeling the collections of microorganisms that are really spherical, i.e. volvox, which is a colony of smaller cells, but it's really spherical. Amazing. And it has been suggested that instead of imposing the distribution of slip velocity on the center of on the sphere itself, you should, to be more biologically realistic, impose the shear stress distribution, not the velocity, so that you wouldn't be in any danger of overtaxing the
I see.
the
Yes.
organism. Do you could you speculate on what such a change of boundary condition would have on your predictions?
Yes, that's a very good question. Yes, yes. I have thought about this. I actually John and we have been discussing this a lot. So we call it. I've been calling it different kind of. To me, it's different kind of ensembles. So because we're fixing different variable in the conjugate variables. So here, what I show is have been showing, as you see, is fixing the swing velocity, is fixing the slip velocity on the sphere, right? And that means the swing force actually is changing over time depending on how close they are, right? But on the other hand, as you said, I could instead fixing the swing force or the swing stress, right? So distribution on that. So that will lead to I think at some point I tried, I didn't try too much with it because so far I couldn't find a very effective algorithm to do it. So I have to solve. So right now the way I do it is I have to solve the velocity first for every particle. So computationally, kind of, I need to find a better algorithm. So I only tried a little bit with it. And it seems that it only changes the time scale of the simulation results, but the qualitative features of the simulation seem to be almost the same. So I would speculate, yeah, I would speculate that that's what's happening. So if I fix the swing force, right, then the particles when they approach each other, they will be slower and slower, right? Because when they get closer and closer, the drag becomes larger and larger. So if I keep the same propulsion force, then they slow down eventually. But that's a dynamic slowdown instead of how to say, if I maybe put it in this way, if I rescale the time variable, then the equilibrium configuration may not be affected. So that's what I'm speculating.
That's fair enough. As an off-the-cuff answer, it'd be worth, maybe you can get one of your brighter students to do it.
Oh yeah, that would be great. Yeah. Yeah, I need to find
You've
the
done it.
better
You've
way
done
to
enough
solve them.
that even an undergraduate project would be, I think even undergraduates would be able to do it with the background that you've supplied. Anyway, thank you very much. Good talk.
Thank you, Tim.
There is a question. There are two questions from the chat. From Wu. Very nice talk. Could I ask two questions? The first is, do you see coupling between translational and rotational motion? And the second is, during collision, could particles touch each other? Would the lubrication pressure keep them away?
Okay, so the first question, yes, if I include the full hydrodynamics, if I include both, right, which is probably what you have in the experiments, yes, they are coupled, but they are coupled in the same sense as they are coupled in active Brownian particles, right? Because the orientation of the particle is going to determine which way they are moving, and that will affect the subsequent dynamics. But I think that's the same. Yeah, in that sense, they are coupled. But there's no other like special, and there's nothing special about hydrodynamics here. And can you repeat the second question?
The second, during collision, could particles touch each other? Would the lubrication pressure keep them away?
Yeah, that's a good question. I think that's related to what Tim was asking me about the fixing the force and so on. That's a very good question. So again, in this model, we are fixing the surface slip velocity, right? So the particles can actually come into touch with each other. So before the two such stealth swimmers touch each other, nothing happens. It's only after they touch, then, yeah. But of course, you can have a soft sphere interaction, right, and so on. You can change that. But yes, here, lubrication does not slow down the particles. That's the answer. And as Tim was suggesting, and it's a very good suggestion. Basically, we can also think about the other ensemble, right? Instead of fixing the swim velocity, right? We can also fix the swing force of these particles. And maybe what's happening in reality is maybe somewhere in between, like the swimmer is fixing a power, right? Swim power rate, right? Output rate. So it's not it's then we need to fix the product of F times V, right? So yeah, so I think that's a lot of more a lot more of interesting questions can be asked. Yeah. Yeah, but here the lubrication does not slow down the particles. They swim at a fixed velocity. Yeah.
Okay. So now thank you for the speaker and I will stop recording now.